In the last section, we put together a recursive solution to the Fibonacci function, and I got to reveal some of my baggage around recursion. I'm just kidding. Anyways, in this video, we're now going to continue by discussing some of the performance characteristics of this recursive solution right here compared to the previous iterative solution that we put together. So really quick, while we still have the recursive solution implemented, I want to flip on over to our tests running in the terminal. You might have noticed that for each test that we're running here, so here's one test, here's another, sometimes we can see the amount of time that that test took to execute printed off to the right-hand side. If the test takes less than 1 millisecond, the time is not printed. So if we run it again, we might see that some of these tests randomly appear to take slightly longer than 1 millisecond. But most interestingly, you'll notice that when we tried to calculate the Fibonacci value for 15, it ended up taking just over 1 second total. And so that's kind of surprising because we've got 1, 2, 3, 4. These all appear to have been computed rather quickly, like right around 1 millisecond. But then by increasing up to 15, it took about 1,000 times longer to compute. Really, 1,000. Here's 1 millisecond. Here's 1,000 milliseconds. That's 1,000 times longer. So what's going on here? Why are we seeing such a dramatic increase in time for such a small increase in the value that we're trying to compute? Well, let's look back at our diagrams a little bit and try to figure out what's going on. Okay, so here's the diagram that we were looking at just a second ago of a call to the Fibonacci function with 5 as the argument. So when we called Fibonacci with 5, the Fibonacci function itself is being invoked many, many times automatically. So each of these boxes right here represents one function call to Fibonacci during or with a recursive solution. So let's count these out. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we've got 15 calls to the Fibonacci function with Fib5. Let's now compare that to the Fib6 function call over here. So notice how Fib5 is still right over here, and we just said that that was 17 calls total, or 15, whatever it was, I already forget. So we can imagine this is 17 calls or whatever it was, and then when we also add in this additional Fib4 right here that we have to call, because we're now dealing with Fib6, we now have an additional 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 calls. So 17 calls for Fib5 and then 27 total for Fib6. This is what we would refer to as, back over here on our diagram, exponential runtime. So for each additional element that we add into our collection, or for each increment of the value n to our function, we are experiencing a dramatic increase in the number of function calls that are required. Now, in my notes right here, I say very clearly, oh yeah, the processing power required doubles. As we just saw, it does not exactly double. It actually slightly less than doubles, but the idea is still very similar here. For every additional element, we are getting a dramatic increase in the number of function calls, or essentially operations required to calculate our value that we're trying to determine. So our recursive solution that we're working with right here is what we would refer to as an exponential time solution. Remember, like we said a moment ago when we were first discussing exponential time, any exponential time algorithm you create is an automatic no-no. We never, ever want to accept an exponential time algorithm as a solution to an interview question. If you came up with this solution right here, and then your interviewer said, gee, how long would this take to run if you put in like fib of 50? And you said, oh, I don't know, but whatever, we can probably just sit around and let it wait. Well, Fibonacci of 50 is going to take an extremely long time to be calculated. So be aware of that. Anytime we start seeing a exponential runtime function, it usually means that there's a different solution we can put together that might be much more efficient in nature. So in this particular case, let's say that you were sitting with your interviewer and they said, hey, give me the recursive solution to Fibonacci. And you came up with this right here. They very likely will say to you, hey, what do you think the runtime of this would be? And the answer that you want to give is, well, it's definitely going to be exponential, because for every increase in n, we are going to get a dramatic increase in the number of function calls that we get. So here's what's going to happen next. Okay, we've discussed everything to that point. the next thing your interviewer is going to ask you is, okay, well, is there any way we can improve this recursive solution here to not be exponential runtime? Is there any way we can, put in some additional fix here to make sure that it is not exponential runtime? And you might say, oh, well, we could do the iterative solution, which we already discussed was linear runtime. And you know what, maybe they'll let you get away with that. But if your interviewer says, is there anything we can do here to improve the runtime of this algorithm? They are looking for you to say something very particular, okay? Here's what they're looking for you to say. They want you to say, well, I'm looking at all these different function calls because we know when we call like fib with 6, we're calling Fibonacci all these different times. And when you start to look at this chart right here, you start to realize that the function is being called many times with identical arguments. So for example, here is fib3 being called one time over here. Fib3 also gets called right here and right here. Here's fib2. Fib gets called with 2 over here, over here, over here, and over here. So clearly, our Fibonacci function is being called multiple times with identical arguments. I've taken the liberty of kind of graying out a lot of boxes here, and I just realized I missed one. Let me do this one too. So all these grayed out boxes that you see are duplicate calls to the Fibonacci function with identical arguments. So if there is some way that we could avoid all these extra function calls, then if we called Fibonacci with 6, we would really only have to worry about doing all the computation stuff for fib 5, 4, 3, 2, 1, and 0 exactly one time. And then all the other times, maybe we could figure out some kind of clever solution there. So in other words, or let me kind of cut to the chase here and say, when your interviewer asks you if there's some way to improve the runtime of our solution, what they want to hear is this word right here. Now, the bad news is that I can't pronounce this word. I'll be honest with you. It's like, I can't even, it's Memoization. Go look up the pronunciation on Google. Memoization. For whatever reason, I just can't do it. Anyways, this is a term for something that we can do with a function call that essentially does this right here. So when we memoize a function, there we go, that's it, memoize. When we memoize a function, we are going to record the arguments of each function call. So we're going to record the arguments, we're going to run the function, and then we're going to store the result of that function call. So we've got some like little table in memory that says, hey, our function was called with this number, and when it was, it returned this result. And then here's the key. If that function ever gets called again with the exact same arguments, rather than running the function again and doing the entire recursion process, all that crazy stuff, rather than duplicating all those results, instead, we are going to return that result that we had computed previously. So what does that look like in practice? Well, basically, just like we saw in the diagram over here, we're going to say, okay, whenever we try to calculate fib 6, we're going to immediately make a call to fib 5. That's going to make a call to fib 4. And so this is the first place where it's actually meaningful, okay? So let's concentrate on this right here. So we're going to call Fibonacci with 4. You and I are going to write some code that is going to say, oh, it looks like our Fibonacci function is being called with an argument that it has never been called with before, which is 4. We will then run the Fibonacci function with 4. We will take the result from that and we will store it in some special location. And so you and I will know that if Fibonacci ever gets called with 4 again, we have already run that situation. We've already ran that scenario. We don't have to execute the function again. So if Fibonacci is ever called again with the number 4, we're not going to run the function itself. We're going to go off to that special place in memory and retrieve that pre-computed result. And so in practice, here's Fibonacci 4 over here. After we do that kind of caching layer, as soon as we go over here and see Fibonacci 4 over here, we are going to say, oh, we don't have to do the recursive call here. We don't have to go through all these additional function calls. We've already ran Fibonacci with 4, and we already know what the value or what that should be returning. And so let's just return that right away rather than spawning all of these additional function calls. So by doing this memoization process or by caching all the results that come out of the function, we can dramatically dramatically improve the run speed of this function. Now, the one thing I want you to be aware of here, this is the very exact answer your interviewer is looking for if they ask you, how can we improve the runtime of this recursive solution right here? They're asking you for a memoized solution. Now, this is not something that's only applicable to Fibonacci. There are many other interview questions, or algorithmic questions, I should say, that can be answered through this exact same memoization process. So this is a great little tool to have in your back pocket, because I can almost guarantee you, you will have an interview with someone who says, hey, this function looks really slow. How can we speed it up? And one of your first tools that you want to reach for in that case is this memoization thing. Okay, so enough talking about memoization. Let's take a quick break. We're going to come back in the next video, and we're going to write some code to memoize this Fibonacci function right here. So I'll see you in just a minute.